Hello, I'm Panini, and today I'll be explaining about depth first search. Let me present my screen first. Okay, so before we move on to depth first search, we'll first understand what a graph data structure is. Graph data structure, it's a nonlinear data structure which consists of vertices and edges. Here, we can use graph data structure for representing social networks and road networks. What are social networks? Consider the case of Facebook, Instagram, or any other social media platform. It helps in networking people. In this case, suppose person A knows person D and C, and person B knows person F and G. It can recommend D to F because A and B are mutual friends. That is one application of this social network graph data structure. The second application is in the case of road networks. Suppose this is some road network. I can represent this road network as a graph data structure. So each of these places, place A, B, C, up to place H, are connected by using this edges. So these A, B, C are all called vertices, and these vertices are connected by edges. So using this road network, I can find the shortest distance between two vertices, say vertex A and vertex H. These are few of the applications of graph data structure. Now, how do we represent these graph data structures? Now that we understood it can be used in social networking, and it can also be used in representing road networks to find shortest distance, to find if there's a closed loop or anything like that. How do we represent this graph data structures? We can represent this graph data structures by using an adjacency matrix. Now, what is an adjacency matrix? Here is an example of a graph data structure. This is an undirected graph. That is, these are not directed, like so you can move from vertex 1 to vertex 2, and vice versa, you can move from vertex 2 to vertex 1. So these are undirected. If it is directed, like if it is like this, that means you can only move from vertex 1 to vertex 2. Now, how do I represent this graph data structure? So 1 is connected to 2 and 3. So 1 is connected to 2 and 1 is also connected to 3. So these two are represented by 1s. Rest all it is not connected, so hence it is represented by 0. So I essentially write all the nodes here, or all the vertices here. So there are 5 vertices. So I write all the 5 here and all the 5 on the top. So I'll represent each of the connection of that particular vertex with its neighboring vertices by 1. So in this case, 1 is connected to 2 and 1 is connected to 3. So these two are 1 and 1, rest all are zeros. 1 is not connected to itself. Like at least you take a 0 in this case. Now, if we consider 2, it is connected to 1, 3, and 4. So 2 is connected to 1, 2 is connected to 1, 2 is connected to 1, 3, and 4. So 2 is connected to 1, 3, and 4. Similarly, we write for other vertices. So if you can see here, we have a matrix. This entire thing is a matrix. What is the order of this matrix? Suppose we have n vertices. The order of this matrix is n cross n. Okay, now you have understood what the adjacency matrix is. But is adjacency matrix the most optimal way of representing, or is there a better way? So why do we have to search for a better way of representing a graph, and why not use an adjacency matrix? So if you can see here, while modeling a social network for say 1 million people, so suppose in a region we have 1 million people and you're trying to model them using a social network, what will be the dimensionality of the matrix? It will be 1 million cross 1 million. 1 million cross 1 million. Oh, that's a huge, it's a huge, so it's a huge matrix. So computing any, or using it for computing any other matrix, or like inverting it or performing any task, any linear algebra task on it, will become very difficult. It's computationally very expensive. So we are essentially trying to find better ways. One way of finding a better way is by breaking down this problem. So if you can see, a person actually knows only a few people. If there are 1,000 people in this locality, he'll only know like 20 people, 30 people, or 50 people. So for person one, instead of writing, if he knows all the people in that locality, we only write the people he knows. So that is where we'll come to the concept of adjacency list. So if you can see here, so person one actually knows only 2 and 3. So we write a list here, 1, 2, and 3. This is an adjacency list, or the list of vertices which are adjacent to vertex 1. 1 is connected 2. Now 2 is connected to 1, 3, and 4. 2 is connected to 1, 3, and 4. So we have a list here. So this is a lot easier to handle, and computations performed over this list are less expensive. So we tend to use adjacency list over adjacency matrices. Now, we have studied about what a graph is, its application, then its applications related to social networks, its applications related to road networks, finding the shortest distance between two places, or recommending one person to the other person. So for all of this, we need to, we have also seen how to represent a graph. For all of this, we actually need to do something to perform all these operations, or to have all these applications. We need to do something called as graph traversal. Graph traversal is the process of exploring all the vertices. So we first need to know how each of these graphs are connected. Then only we can perform, or we can recommend a person to other person, or if we know how two vertices are connected, how different vertices are connected in the graph, then only we can actually find the shortest distance between different vertices. So it is essential for us to know how each of these vertices is connected. So we need to explore each of these vertices. So that is graph traversal, the process of exploring all the vertices in the graphs. So you start from some vertex, you explore all the vertices in the graph. That is graph traversal. So you know how each of these vertices are connected. So now with this graph traversal, we'll be able to find the shortest distance between two vertices, or we can see if there's a cycle. So here in this graph, this is a cycle or a closed loop. So for different applications, we need graph traversal. One interesting example of graph traversal, or where it can be used, is in the case of Sudoku. So you know Sudoku, it's an 9 cross 9 matrix. So it can be thought of as an 9 cross 9 matrix, and it has smaller boxes, each of size 3 cross 3, each of size 3 cross 3. Now we can actually model this as, 1 second. Okay, so each of it has 9 of these 3 cross 3 boxes, the entire Sudoku. Now what I can do is, there are some fixed numbers here, 2, some 7, like say suppose there's 1 here. So I can actually model this as a graph. So there is 2 here, it is connected to the next one, it is connected to is here. So I can put a vertex here, again vertex. So here this row condition can be thought of as different vertices connected in a horizontal row. And similarly, I can connect all these other vertices as well. Okay. So this is how I represent a graph of a Sudoku problem, and I can solve it using this. Think about it and think of how you'll be solving this problem. Now, we'll go further. 1 second. I'll just erase this so that we can move forward. Okay. Now that we have understood what graph traversal is, one way of traversing through the entire graph and knowing how different vertices are connected is by using depth first search. Other way is breadth first search, but in this class, I'll be teaching about depth first search. Depth first search. Okay, so okay, depth first search. So this, suppose we start, so in depth first search, you think of yourself as an bold explorer. What does a bold explorer do? Suppose I'm a bold explorer. I start from, say, think of this graph as all the set of doors. I'm at position 1. I have door openings to, this is a tunnel. Assume this is a tunnel. All these are tunnels. I have a door opening to 2. 2 is again a door, 3 is again a door. What would an bold explorer do? Start at 1. I'll see two tunnels, tunnel 2 and tunnel 3, to door 2 and door 3. What will I do? I'll take one of them. I'll go to 2. At 2, I'll open the door 2. I'll see 2 is again, 2 will lead to another 2 tunnels, 3 and 6, or else I can come back to 1. So from 2, I have 3 options, 1, 3 or 6. But remember, I told you're a bold explorer, bold and confident explorer. So you'll never come back. You'll want to explore the entire graph first. So from 2, you'll either go to 6 or 3. Okay, and we continue and so on. So suppose we go to 3. Now again, you'll have 3 doors, to 4, to 2 and 1. You're a bold explorer, so you'll not go back to 1 because you already saw 1. You already saw 2. That is where you came from. So you'll not go back. Since you're bold, you'll go forward. You'll try to take that risk, or you want that kick. So you will go to 4. And that's how graph depth first search works. So here I'll try to actually explain it more precisely. So you start with 1. Say suppose you start with 1. That 1 is connected to 2 vertices, vertex 2 and vertex 3. So I'll have 2 stacks here, 1 stack on top. This stack represents all the vertices I've visited. The second stack represents all the vertices which that particular vertex or the vertex which you are exploring is connected to. So I start with 1. So I've visited 1, so I'll write 1 here in the visited list. It is connected to 2 and 3. So in the second stack, I'm putting 2 and 3 here. Okay. So now I have choices to go to 2 or 3. I'll go to 2. Suppose I go to 2, I can even go to 3. But I'll tell you what happens. So I can either choose 2 or 3. We'll go in other order after some time. So let me go to 2. From 2, again, I have 3 choices. Again, now suppose I'm at 2. This green color represents where I am currently. So I'm at 2. So I'm exploring 2. So I write down 2 here. It is connected to 1, 2 is connected to 3, and 2 is connected to 6. Now I'm a bold explorer. I'll not come back to 1. I'll write what it is connected to, but not explored. So 3 and 6. So I write 3 and 6 in the stack. Remember, for this 2, what it is connected to, those only you write in the second stack. Now what do I do? The topmost element in this stack has to be explored. Like after 2, I will not come back to 1 because I'm a bold explorer. So what is the topmost element of this stack? 3. So I'll come back. So I'll go to 3. So I'm at 3 right now. And from 3, I have 2 choices. I can go back to 2 or come back to 4. Obviously, I'll not go back to 3. I'll not go back to 2. So I'll go from 3 to 4. Okay. So, but in my previous case, since we are at 2, we had 2 choices. We could either go to 3 and 6. So we put 3 and 6 in the stack. So we put 3 and 6 in the previous stack. That is here. Yeah, so we had 3 and 6, but from 3 to 4, so at 2, we had 2 choices, 3 and 6. So we put 3 and 6 here. Now we have visited 3. So 3 comes in here. From 3, we have 1 choice, that is to go to 4. So we put 4 here on top of stack. 6 is from the previous stack. 6 is from the previous stack, and from 3 we are visiting 4. So 4 comes in here. So now what we do? From 3 we visit 4. So 4 you visit, from 3 you visit 4. So 4 comes in here. From 4 you again have 1 choice, you go to 5. So 5 comes on here at the stack, at the top of the stack. So you visit 5. From 5 you have no other place to go. From 5 you came to a dead end, like you have no other place to visit. So what do? You go back from 5 to the previous node which you came back from. So 5 to 4. 4 is not connected to any other vertex, any other new vertex. So you go back, you come back to 3. Now from 3 is not connected to any other new vertex. So there's no other vertex which is connected to 3. So what do? You come back from 3 to 2. From 2, you see if you have visited all the vertices. From 2, now you can see a new vertex, 6, which is here. Now visit 6. So from 2, you visit 6. So essentially you're here. So from 2, you're visiting 6. So this 6 will come in here. So you have visited all the vertices here. This is a visited list. Now the second list is the second stack is empty. Okay. So by using this process, we are able to visit all the by using this process, we are able to traverse through the entire graph or visit all the vertices. And now we know how each of these vertices are connected. And okay, so now you reach 6. From 6, you're not connected to anything. From 6, you're not connected to any other vertex. So what do? You move back to 2. From 2, you don't have any other new vertex to visit. So you go back from 2 to 1. From 1, you don't have any other new vertex to visit. So what happened? So you started from 1, you went to 2, 3, 4, 5, 4, came back to 4, came back to 3, then came back to 2. You visited new vertex 6, you came back to 2 and came back to 1. You've traversed through the entire graph now. And hence you have completed the entire graph traversal. Now so this is one way of traversing through this entire graph. There are other ways as well. Like if you remember, we started from 1, we visited 2. Instead, we could have gone to 3. We could have we started from 1, went to 2, then we went to 3. We could even have gone from 1 to 2 and 2 to 6. All these are valid possibilities of traversing through the graph. We'll see other valid possibilities of traversing through the same graph. Okay. So the first order is a order which we just went through. That is 1 to 2, 2 to 3, 3 to 4, 4 to 5. 5 is not connected to any new vertex. So back to 4, 3, 2, and 6. So 1, 2, 3, 4, 5. And finally coming back from 5 to 2 and 6. So 1, 2, 3, 4, 5, 6 is one valid order for DFS. Second valid order is instead of going to 2, from 1, you come to 3. From 3 to 4, 4 to 5, you come back. Then from 3, you see a new vertex, which is 2. From 2, you visit 6. So 1, 3, 4, 5, 2, and 6 is one valid order. Similar to others, you need not start from 1. You can even start from 4. From 4, you can go to 3. From 3, you can go to 1, then 2, then 6, then come back to 2, then to 1, then to 3, 4, and 5. So 4, 3, 1, 2, 6, and 5 is another valid order. So you can actually go in any order and explore all the vertices. Now, how do I find the algorithm? Like I'll explain the pseudocode to you. So before I get into the pseudocode, one thing you need to notice here is the depth first search, what we are doing right now, is recursive in nature. Why do I say that? Well, look at this. You're starting at 1. You're exploring all the vertices which are connected to 1. Then you go to the unexplored vertex. Now, in the entire example which I explained, from 1 we went to 2. What do? You're doing the same thing. You're exploring all the vertices which are connected to 2. That is 1, 3, and 6. Right? Now, after that, we went to 3. What are you doing at vertex 3? You're doing the same thing. You're again exploring the vertices. So at each vertex, if you see, we are essentially doing the same function. We are exploring it. Correct. And to which vertex are we going? We are going to the vertex which is not explored. Remember the same. Remember the analogy where I told you, imagine yourself as a bold explorer. From 2, we didn't come back to 1. We went to 3, or we could have gone to 6. So we need to keep a list of vertices which we visited. Correct. And at each vertex, so there are two things here. So at each vertex, we are doing the same thing or the same function. That is visiting the neighbors connected to it. At 1, we visited 2 and 3. At 2, again, we are visiting its neighbors. That is 3, 6, and 1. At 4, we visited its neighbors, 3 and 5. So essentially, it's the same task which you're doing at every vertex. So it is iterative in nature at each vertex. So at each vertex, we are performing the same function. So it's iterative in nature. And the second point is at 2, we didn't go back to 1 because we already visited 1. So at each vertex, you go to the next vertex, or you go to the neighboring vertex which is not explored. Remember these 2 points, and we'll devise an algorithm using this. So first, it's iterative in nature. Okay, so you'll have a function call instead of function call. Now you put a list. Say you consider the visited list. Consider a list called visited, where you mark all the vertices if it is visited or not. G of length is the number of vertices. Now put everything as false. That is, you have a list which says every vertex is false. Every vertex is false. That is, none of the vertices are visited. Now we start the depth first search. The function starts here. Given a graph G and the initial vertex, in the example which we took, we started off this initial vertex as vertex 1. 1 dot visited is true. So we are changing the status of vertex 1 to visited. That is true. So your list will be true, comma false, comma false, comma false, true. Everything will be false. Only 1 is visited, so only 1 will become true. 1 dot visited, the status of 1 we are changing to true. Now, what we are now doing is we are looping through the vertices which 1 is connected to. For vertices in 1 dot neighbor, 1 dot neighbor has 2 and 3. 1 dot neighbor has 2 and 3. What do we do? So u dot neighbor is list which is 2 and 3. Correct. So if v dot visited, that is the first element of the u dot neighbor, that is 2, is false. That is, from 1, if you haven't explored this, then you go to 2. That is what the statement is saying. So I'm repeating this again for better clarity. So for v, so for vertices in u dot neighbor, u is 1 here, 1 dot neighbor is 2 and 3. If you didn't visit 2 or 3, then visit one of them. Now, since from 1 you didn't visit 2, you are going to 2. Now you'll do the same thing, depth first search of G comma 2. From 2 again, you will find vertices which are connected to 2, that is 3, 1 and 6. You'll again go back. So this will be, you started off with DFS of G comma 1. You reached here, you will be depth first search of G comma 2. Now G comma 2 will go back again. 2 dot visited will be changed to true. So 2 will be visited. 2 dot visited is changed to true. So you have visited 2. For vertices in 2 dot neighbor, that is 3 and 6, or 6 and 3. Then you visit the unexplored vertices. 2's neighbors are 1, 3 and 6. But 1 you have already visited. So if neighboring vertices, suppose 1 dot visited is already true, so it will not get into this. So 2's neighbors are 1, 3 and 6, but 1 will fail here because 1 is already explored. So you'll go to 3. Now DFS of G comma 3 will be executed. So you'll go to 3, the same step. You'll go to 4 again. So here DFS of G comma 4 will come, then you go to 5, will come back. Okay. So this is how a depth first search algorithm is executed. So it is recursive in nature, and we are doing it recursively. Okay. Now there's one more small point. So you've completed the depth first search algorithm. Why do we need this? In some cases, we have disconnected graphs. So this is one graph. Suppose I have one more graph next to it, like say suppose it ends at 6, so there is 7, it's connected to 8, and 8 is connected to 9. Suppose these two graphs are not connected. Suppose I have, it ends at 6, so I have 7 here connected to 8. I'm sorry. I have 7 connected to 8, and 8 is connected to 9. If you can see, these two graphs are not connected. This is one independent graph, and this is one independent graph. Okay, but we need to traverse through both the graphs. So we run this over all the vertices in the graph. So this entire thing is a graph. These two are individually disconnected graphs. So if we run the loop through each of these vertices, then we visit both, then we are able to traverse through both the disconnected graphs and hence the entire graph. So this is why we have this. Yeah, this is the pseudocode for the depth first search algorithm. Hope you have understood. Thank you.